Welcome to Hartman Math. This is lesson 5.5, graphs of logarithmic functions. So before we get to those graphs, I have to figure out what logarithmic functions are. So example number 1 says we're going to find the inverse of an exponential function that we've previously studied. And for our exponential function, f of x equals 2 to the power of x. Reminder that 2 is the base of that exponential function. So our process for finding an inverse is step 1, write it as y equals, then switch the x and the y, and then solve for y. That kind of creates a little bit of a problem because we've never had to solve for a quantity, a variable that's the exponent. So that's where the logarithmic functions are going to come in. So what we're going to do is we want to get the y by itself. So essentially pull the y down from being an exponent so there's just a normal y. When we pull that down, the 2 kind of gets displaced or pushed out of the way. And the 2 is the base. The 2 is always going to be the base. But now we're rewriting and changing forms. 2 is now going to become the base of the logarithm over here. So the abbreviation for logarithm is log, and then it's going to be, because the 2 is moving over, it's going to be base 2 of x. So it looks like this. It's log with a little 2, so it's a subscript written low and small, log base 2 of x. And that is how we say it. Log, we say the word base 2 of x is equal to y. So the 2 moved over, it became the base of the logarithm, log. And then we just rewrite this back as f inverse of x. So that's the inverse of an exponential function. It's a logarithmic function. Notice that the bases are the same. 2 to the x, log base 2 of x. So kind of using that process, one of the important skills for whether we're talking about graphs or a future lesson of evaluating, investigating logarithms is to be able to rewrite back and forth from one form to another. So here we have an exponential equation. We want to rewrite that into logarithmic form as a log equation. And the secret, it's always going to be move the base. So in this case, 2 is the exponent, and that makes 9 the base. So we're going to take the 9 and move it to the other side. And that means the 2 is going to drop down. We'll have 2 equals. And then we're writing it into log form. 9 was the base, so 9 stays the base. Log base 9 of 81. And that's the equivalent equation now in logarithmic form. It's your turn. Try this one. Pause it here. Hit play when you're ready to check. Okay, so 36 is our base. We'll move the base to the other side. 1/2 drops down. Now normal size. 1/2 equals. 36 is now the base of the logarithm, log base 36 of 6. Can we do the reverse? Take an equation that's in log form, rewrite it into exponential form. I think our directions are backwards here, so we're going to switch those. Rewrite from logarithmic form into exponential form. We're going to move the base. So in this case, the base, the small number, it's 2. So 2 moves to the other side. We're rewriting it out of logarithmic form, so we can drop the log. That means 8 will be by itself. And now the 2 becomes the base of the exponential equation So 2 is now the base, and that bumps the 3 up to become the exponent. 8 equals 2 to the third power. It's your turn. Once again, direction switch, rewrite from log form into exponential form. Pause here until you're ready. We're going to move the base. 27 moves to the other side. We drop the log. 9 equals. 27 is the base, and that bumps the fraction 2/3 up to be the exponent. 9 equals 27 to the power of 2/3. Example number 4, we're going to graph both f of x equals 2 to the power of x and the inverse function that we just found, log f inverse of x is log base 2 of x. We're going to start here. Takes us back to a previous lesson. For exponential functions, we know we need 2 key points. Plug in a 0. 2 to the 0 power is 1. So we got a point at 0, 1. And plug in a 1. 2 to the first power is 2. So 1, 2 is a point. And that's an exponential, so we know it's going to look like airplane taking off. Ends up like that. And this is the inverse function. I don't quite know how to really approach that yet, but we do know about inverse functions, such as that process of switch the x and the y, and that works for points. So this was 0, 1. Let's switch that around. That means 1, 0. And this was 1, 2. Switch the x and the y. 2, 1. Then we want to make sure that our graphs are reflections of each other in this diagonal line y equals x. So make sure that the black graph flips over, and so to kind of get that shape passing through, it's going to need to look like this so that they are mirror images of each other. Now we don't want to have to graph both every time we want to graph a log graph. So for the key points for the log parent function, which is going to look like this, whether it's log base 2 of x, log base 7 of x, log base 10 of x, here are going to be the key points that we're talking about that we need. Okay, and then we'll talk about the shape. But the first one is 1, 0. Because our exponentials always had 0, 1. Switch that around, 1, 0. The second one here was 2, 1, but it's 2 because 2 is the base. If the base was 5, it would be 5, 1. It's always going to be second point for our log graphs, parent function, base, 1. Whatever the base is, that, 1. And then you can see that we're bending. We're getting very, very close to, what are we getting close to? Getting close to the y-axis. So let's take a look at just the log graph and look at its key characteristics. So here's our graph. Here's our function. I'm talking about the log function, particularly base 2. What's the domain? Well, it's not negative infinity to positive infinity. There are no points over here. Yeah, it's going to positive infinity. What about left? Well, it keeps getting closer and closer and closer to 0. So it's everything to the right of 0, parentheses, because it doesn't touch 0, 0, infinity. Now the range, how low? Negative infinity. How high? Positive infinity. So the range is negative infinity to positive infinity. Where is it increasing? Well, it's increasing on the whole domain, but that's the domain. If it's not increasing over here, there's nothing over here. So it's increasing from 0 to infinity. Or is it decreasing? Well, it's never going down. So we don't have that. And once again, what did we get really, really close to? The y-axis. What's the equation of the y-axis, which is a vertical line? All vertical lines are x equals number equations. X equals, it passes through 0. So x equals 0 is the equation of our asymptote. What about the end behavior? As x approaches infinity, as we go to the right, where are we headed? Slowly, but still going up, up, up forever. And this one kind of reversed it. We said, well, the function is going towards negative infinity. What was x going towards? Well, let's take a look. Where is it? Where is our graph going towards negative infinity? Right here, going towards negative infinity. What is our x getting close to? It's getting close to our asymptote at 0. Example number 5, draw the graph of the parent function. We'll draw that dashed or dotted. And then the graph of our final function, solid, 2 points. That's our approach. So our parent function, again, stops at the x, log base 4 of x. Back to the previous slide, the 2 key points, 1, 0. Base, 1. Our base is 4, so 4, 1. And then it's going to get close to, but not touch, the y-axis, bending like that. It only bends in one direction. No, it doesn't go flat. It keeps going up. All right, now we got to do some transformations. We got to translate. We got to shift right here. What does that do? This is outside of the log function, so this is the k. So we're going to go up 4. So, key points, 1, 2, 3, 4. 1, 2, 3, 4. Asymptote, y-axis, is going to go up 4, but that doesn't really change anything. We only need to redraw it if it moves left or right, because that would be a different asymptote. So we're fine here. We go through these 2 points, get close to our same asymptote. That asymptote is x equals 0. And that means the domain is everything to the right of that from 0 to infinity. Parentheses, because it doesn't touch 0 ever. And the range, down forever, up forever. Negative infinity, positive infinity. Example number 6. Same ideas. Let's see. All right, let's start with the parent function. Oh, it's the same parent function. What are the key points? 1, 0. Base, 1. 4, 1. Gets close to, but doesn't touch the y-axis. Transformations. What's happening here? With the x. In parentheses. Think opposite. Go to the right 2. And also shift, translate. That's our k. That was our h. This is our k, down 3. So we're going to take our key points, right 2, down 3. Right 2, down 3. Asymptote, right 2, down 3. Well, the down doesn't do anything, but the right 2, we have to redraw the asymptote dotted. Because our graph can't cross it. If we don't draw it, we might just do this. We can't cross this. So we got to get close to without touching the new asymptote. So same exact thing, shifted right and down. So there's our graph. Asymptote, we redrew it. X equals 2. So the domain is connected to that asymptote. It's everything to the right of 2. Not touching 2. Parentheses. Range, down forever, up forever. Negative infinity to positive infinity. Try this one. It's your turn. Pause here until you got graph, parent graph, final graph, asymptote, domain, range, and hit play when you're ready. So our parent function, log base 4 of x, so 1 comma 0. Base comma 1, 4 comma 1. Gets close to the y-axis. It's our transformation inside parentheses with the x. Think opposite. We'll go left 5. So we're going to take our key points, left 5, left 5, asymptote, left 5. 1, 2, 3, 4, 5. So now we're redrawing, getting close to the new asymptote. Make sure it still goes up. Don't go flat. Asymptote, x equals -5. Domain, to the right of -5. Range, log functions always go down forever, up forever, negative infinity to positive infinity. That's it for today. I'll see you next time.